So the first talk will be by Duncan Dauvergne. Duncan, do you want to share your screen now?
Yeah, sure.
Okay. So Duncan is coming to us from, well, it could be anywhere in the world, but I assume Princeton.
It is still Princeton, yes.
Okay. And he'll talk about the Airy sheet.
Okay, thanks. Thanks for the invitation. So I will go ahead and get started then. So this is based on joint work with János Ortman and Bálint Bírák. So we're going to be working with a model of last passage percolation called Brownian last passage percolation. So I'll start by explaining the model. So I'm going to have a sequence of n independent Brownian motions. Okay. And then I'm going to consider a function pi from an interval xy to the set 1 up to n. And for our purposes, pi is always going to be non-increasing. Okay. And then I can define the weight of pi with respect to the Brownian motions b in the following way. So dB of pi is going to be, I'll write the formula and then I'll explain what I mean. So it's the sum from I equals 1 to n of bi of pi I minus bi of pi I plus 1. So pi I is going to be the time when pi jumps from line I to line I minus 1. So I've drawn a sample path pi in the picture. So you can see pi at x, it's starting at n, and at y, pi ends at 1. And what dB of pi is you just sort of superimpose the graph of pi on these Brownian motions, and we're going to collect all of the increments here. So for example, at bi, we jump up to line I at time pi I plus 1 and jump off at time pi I, and you collect the increment bi of pi I minus bi of pi I plus 1. Okay. So that's the weight of a path. And then the last passage value, Brownian last passage value, b from x to y, is the maximum of dB of pi, where this max is over all pi going from xy to 1n, which are non-increasing. Okay, so this is the Brownian last passage value. And if a path pi achieves this maximum, I'm going to call that a geodesic. Okay, so this is a model of last passage percolation. You can think of it either as a random growth model or in some sense, as a model of a random metric, except instead of in a random metric, you'd be looking at minimal length paths. Here we look at maximal length paths. Okay, and it lies within the KPZ universality class, and it's a particularly nice model. It's integrable, and we can say a lot about it. So what I'm going to talk about today is the following theorem, which is, okay, due to myself and János and Bálint. So first, let me define the scaling. So I'll let Sn of xy. This is going to be the Brownian last passage percolation value. I'm using the superscript n to indicate that we have n Brownian motions from 2x n to the minus 1/3 to 1 plus 2y times n to the minus 1/3. And then if we subtract off a mean term and rescale, then this object converges in distribution. So the mean term is 2 root n plus twice y minus x n to the 1/6. And then we need to rescale the entire thing by n to the 1/6. So then Sn converges in distribution to a limit S. So S is a function from R2 to R, and it's continuous. And this S is the Airy sheet. Okay, and I won't talk too much about the type of convergence here. It's a functional convergence. So you can think of these as living in the space as random continuous functions from R2 to R with, say, the topology of uniform convergence on compact sets. Okay, so I'm going to focus on this today. A couple of things to note about S are the Airy sheet is a fundamental limiting object here. So in particular, you expect that S is a universal limit. So right now we've only proven this for Brownian last passage percolation, but you expect to see it in all sorts of random growth models in particular, and it's a work in progress that this should also be the limit of, say, exponential geometric last passage percolation, other nice integral models. Another thing you can do is, what we've done here is just take the scaling limit of Brownian last passage percolation, where we're varying what I'm going to call the spatial coordinates, but you could also vary the line that you start on, and then you'd have 4 parameters to vary. And it turns out you can build this 4 parameters limit from S. So you can build the 4 parameter scaling limit from S. And this is the directed landscape. And just like you can build the scaling limit of all last passage values, you can also use the Airy sheet as a fundamental building block to get the scaling limit of the geodesics. Okay. But what I want to talk about today is just give some sense of how we prove this theorem here. So the usual approach to, or sort of the classical approach to KPZ limits, certainly with Brownian last passage percolation, is there are many things that can be expressed here through formulas. So there are nice formulas for the last passage value between 2 fixed points, or between 1 fixed point and 1 endpoint, where you're allowed to vary that endpoint along a line. But there aren't, okay, as far as we know, there aren't nice formulas for the last passage value between 2 endpoints, as you're allowed to vary both of the endpoints. So our approach to proving this theorem is a little bit different. It doesn't rely, we use formulas as a starting point, but we aren't actually able to obtain explicit formulas for this S. So you need a different route. But I'm going to start with this classical approach to Brownian last passage percolation. So this is, I'm essentially going to describe a continuous version of the RSK correspondence, for those who are familiar. So I'll extend the definition of last passage in the following way. So I'm going to let bk from x to y be the maximum over the sum from I equals 1 to k of dB of pi I, where here the max is over all sets of disjoint paths pi I from xy to 1n, which are non-increasing. So a sample set of paths is kind of drawn here. So this would be with k equals 4. So the disjointness condition is disjointness on the open interval xy, if you will, in the picture, because we're allowing them to kind of share endpoints. So you imagine that you have geodesics which are attached, where they're not going to be geodesics, but you're optimizing over paths with the same start and endpoint, but they have this enforced disjointness condition. okay? And then with this definition, we can create a map, which I'll call the Milind map from B to W. So it's going to send the Brownian motions B1 to Bn to a sequence W1 through Wn, which we define in the following way. So each Wi is going to be a continuous function from 0 infinity to r. And W1 has a simple rule. So W1 of y is just the Brownian last passage value from 0 up to y. Okay. And then the others you define in the following way with this sum. So the sum from I equals 1 to k of Wi of y is the k-fold last passage value from 0 to y. Okay. So for example, you can think of W2 is how much extra weight you can get by adding in an extra disjoint path. And what you can at least kind of imagine, though this is not a proof, is that you're going to get diminishing returns from adding each one of these extra disjoint paths. So in particular, this means that the W's are ordered. So deterministically, you have W1 greater or equal W2, and so on all the way up to Wn. So this is deterministic. And other than the fact that they're all 0 at the start, these inequalities are actually almost surely strict everywhere for Brownian last passage percolation. So this is kind of how I imagine this B to W map is you start with unrelated independent Brownian motions, and then you can send this to W1 through Wn, and you can superimpose the graphs of W1 through Wn on top of each other, and then they're ordered in this way. And this is why we get this term melon, because these kind of resemble stripes on a watermelon, maybe if I add a few more in. Okay. So what's nice is that this W1, it's clearly encoding some information about the last passage value. So in particular, it encodes last passage values from 0 up to a point as you vary that point. And it has a very nice structure. So this is a theorem due to O'Connell and Yor, which says the following. So W has the law of n non-intersecting Brownian motions. So n Brownian motions conditioned all with the same starting point, conditioned never to intersect. Okay, so you need to condition in some limiting sense. Or alternately, W is the eigenvalue process of Hermitian matrix Brownian motion. And both of these representations are really nice. So the fact that it's non-intersecting Brownian motion, so you can, you have the Carlin-McGregor formula for non-intersecting Brownian motion, so you get nice determinantal formulas for the probabilities that the Wi's are in particular places. And so W is really amenable to asymptotics. And so let me give sort of the strongest asymptotic result you can say about W. So again, I'm going to first define the rescaling. So I'll let A-N-I of y be W, again, n indicating that we have n Brownian motions, Wi from at 1 plus 2yn to the minus 1/3. And then again, we subtract off a mean term, 2 root n plus 2y, and rescale by n to the 1/6. So then this an sequence, which I'm going to call an1, AN2, AN3, and so on, this converges to a limiting object A, which is A1, A2, and so on. And A is the Airy line ensemble. So this will be sort of very familiar for those who were in Ivan's course earlier in the week. Okay, so this theorem about Milind asymptotics, sort of for a single point, proving this for Brownian last passage percolation, doing this for I equals 1 and y equals 0, showing that this converges, was done in two separate papers by Grabner, Tracy, and Widom, and Baryshnikov. And then sort of constructing the Airy line ensemble in terms of its finite dimensional distributions is due to Prehofer and Spohn. And the definitive version of this theorem in terms of getting functional convergence and distribution here is due to Corwin and Hammond. So this is kind of the picture of what's happening here. So I look at my Milind W, okay, and I look at a window around time 1, and I have an order n to the minus 1/3 spatial window and order 1 number of lines here. And then this, after subtracting the appropriate mean term, converges to a limit A. And you can think of A as a collection of a collection of infinitely many non-intersecting Brownian motions with sort of some rules for how they behave as time goes to plus and minus infinity. Okay. Okay, so the question is, sort of say, what does this tell us about Brownian last passage percolation? So again, I have this formula that W of y, or W1 of y, is the Brownian last passage value from 0 up to y. So this is what it's going to tell us something about. So I have my starting point 0, and I'm looking at all last passage values to this top in an order n to the minus 1/3 window here. So I'm just going to shear and scale this picture. And then after I shear and scale, I get an object that looks sort of like this. So if you draw geodesics to multiple points from a starting point 0, you see this tree structure, right? So the geodesics like to stay together for a while to pick up good portions of the Brownian motions, and then they split off at some point after that. And so what this Milind asymptotics result, this Airy line ensemble, tells you the joint scaling limit of all of these values here. And also, that's just for the top line. Also, you have other lines below. So it's also telling you the scaling limit of last passage value of these multipath last passage values that look something like this. Okay. This is how you can kind of visualize this result. And so you might think, well, it seems like this is telling us, you might ask, is this telling you anything more? So for example, if you know that the last passage value to this point is large, that tells you that somewhere along a geodesic path, there's some good portion of your space. So there's some good portion of weights that you're allowed to pass through, okay? And similarly, if a last passage value here is small, it tells you that that part of your space is somehow lacking. And so you might say, well, we know a lot of different last passage values. We know a lot of multipath last passage values. Maybe we're able to understand enough of our space in this way that we can actually extract more information. And it turns out this is the case. So what you can do is you can from the Airy line ensemble, if you fix a point here, so this is xn to the minus 1/3. So in here it would be xn to the minus 1/3. It turns out that the Airy line ensemble also contains the last passage values from this point xn to the minus 1/3 like this. In a really kind of complicated way, but this is the key to getting convergence to the Airy sheet. So let me explain how this works. How do you get last passage values from a point other than 0? So the starting point for this is a kind of interesting combinatorial identity. So, which is quite surprising the first time you see it. So maybe let me. So for any x less than y bigger than 0, the last passage value across the Brownian motions from x to y is actually the same as the last passage value across the Milind functions from x to y. So remember, we're starting with n Brownian motions, and then you have this map. So you're taking a set of n functions to another set of n functions. So it's still perfectly reasonable to define last passage across these functions, though you might not think it has any interesting content. But it turns out this is the case, that b from x to y is always the same as w from x to y. So this is the kind of picture in the scaling coordinates. As I start with my environment of lines, and this last passage value is the same as last passage across the Milind between the same points. Okay, and for this identity, so this when working on the paper, this was sort of discovered independently, but it turns out that this actually goes all the way back to a paper from the early 2000s of Bian, Bougerol, and O'Connell. And there's sort of another related paper of Nomi and Yamada that also, again, independently of the Bian, Bougerol, and O'Connell paper, also essentially obtains this result, though they don't quite state it in those terms. So you might think, well, is this good for anything? So we know that the Milind is nice. Okay, it's non-intersecting Brownian motions, but why would last passage across Brownian motions conditioned not to intersect be simpler than last passage across Brownian motions with no conditioning whatsoever? So you should expect that. So you shouldn't necessarily expect that this is much of an improvement. But what turns out to be the case is at the scales we're looking at, the branching structure of geodesics in the Milind is much simpler than the branching structure of geodesics here. So it turns out, so at this order n to the minus 1/3 scale, the branching structure in the Milind is simpler. Okay, so this already makes you hopefully think, okay, if you can understand the branching structure is simpler, maybe it's going to be easier to take limits this way. So why would this be the case? So let's start with the simplest thing, which is just geodesics from 0. So in the original Brownian motions, if I look at the geodesics from 0 up to the top line, I see this kind of complicated tree structure. And now I could ask, well, what do those geodesics look like in the Milind? So now 0 is here, and I have a bunch of non-intersecting paths like this. And because of the non-intersection structure, there's never going to be any reason to use any of these lines other than the top line when you're creating a last passage path. So the optimal last passage strategy in the Milind is jump up to the top line and stay there. So the geodesics here just all follow the top line. So I just have my one geodesic following the top line up to 1, and then the others just go a little bit further than that. Okay, so So the upshot is, we had a complicated branching structure here where there's lots of branch points and they're all happening in the bulk. And in the melon, everything became completely trivial. So you might think, well, this is only so interesting. We already know that the melon contains the last passage values from 0. That's kind of straight from definition. But now you could think, well, let's look at a point x n to the minus 1/3, which is pretty close to 0, but not exactly equal to 0. So again, what's going to happen here is when x is pretty close to 0, typically, if you look at the geodesics from x n to the minus 1/3 up to these points here, they'll join up with these geodesics from 0. Okay, and so other than some discrepancy at the bottom, these last passage trees are exactly the same. So in particular, what this tells you is in the picture, the Brownian last passage value from 0 to z minus the Brownian last passage value from 0 to 1. This is equal to the same thing as the Brownian last passage value from x to z minus the last passage value from x to 1 for all z in, say, 1. Maybe I'll give this guy a name. I'll call this 1 plus z naught n to the minus 1/3. For all z in 1, 1 plus z naught times n to the minus 1/3. So as you vary z, these increments are the same. And we know that this is also true in W by this identity, by this nice combinatorial identity. So now you can think, well, what does this mean about the last passage, or about the geodesics in W? So I'll first draw my geodesic up to 1. Maybe it does something like this. You could think, well, how could the increments of all of these geodesics starting from x n to the minus 1/3 be the same as the geodesics from 0? Well, basically, just like in this picture, they're going to need to share the same part of the path. The sort of differences in the paths are going to need to be exactly the same. So what that means is if I look at my geodesic from x n to the minus 1/3, not to 1, but to a point later on, so this is sort of 1 plus z for some z in the middle, then it has to follow this exact same path and just extend a bit further. So these green dots need to be doing the same thing as the red dots. Just like the geodesic changes in the original Brownian picture were the same from x and from 0, they need to be the same in this melon picture. So the point is, in both cases, the branching structure, so in this case, the branching structure from x to this interval becomes trivial in the melon. So the branching structure from x n to the minus 1/3 to this interval is trivial in this melon W. Now this is not generally the case. So the thing that we did here is we chose x that was sort of close enough to 0 so that we saw this effect. But if x is far away, but still on this order n to the minus 1/3 scale, then you don't expect these things to have the exact same branching structure. But it turns out that the branching structure in the melon is still much simpler than it is in the original Brownian motions. So now this is sort of, you can imagine this being a larger gap between 0 and x in this next picture. And I have, say, some branching structure here. When I go into the melon, I may have some other branching structure that looks like this. But and all of these points are in the bulk of your Brownian motions, all these branch points get sent to the top corner. So they get sent to an order 1 region here and an order n to the -1/3 region in this direction. So in the extreme case before, all the branch points were getting pushed onto the top line. Here, all the branch points are just getting pushed into some top corner. Okay, so rather than your branching all taking place in the bulk, like they do in the original Brownian motions, they're taking place in the top corner. Okay, so this is a complicated thing to prove, but hopefully it's at least believable given this picture up here. So what is this good for? Well, we know that the top corner here converges to the Airy line ensemble. Okay, so this is the object that converges to the Airy line ensemble A. And all of the interesting branching information here is happening in this top corner. So that really suggests that the last passage values from xn to the -1/3 up to different points here should be contained in A. So for example, we can do the following thing. So if I say I wanted to look at the difference between the melon last passage value to this point and this point. So that's just the difference between this and this guy here, which is just the same as the difference between the last passage values, not starting at the base xn to the -1/3, but starting at some point in this top corner. So I have w from xn to the -1/3 to 1 plus yn to the -1/3 minus w xn to the -1/3 to 1 plus zn to the -1/3. This is equal to the same thing from some point star, where star is in the top corner. And in fact, you can let this, if you kind of look at the picture, our choice of this star is not quite unique. You can choose any point. Maybe if I zoom in on this picture a little bit. So this choice of star, I could have chosen any point along here. And what's more is, if I don't quite choose a point on this path, but I just choose a point which is pretty close, then it's likely that we're going to connect up and the differences will still be the same. So if you can estimate the location of this path pretty well and choose a deterministic point which is close by, you might be able to express this difference in terms of a difference of 2 last passage values from a deterministic point, which is now sitting somewhere in the top of this melon that converges to the Airy line ensemble. Okay, and so this is the key thing which allows us to get the Airy sheet. So let me express, I'll write down what the Airy sheet is in terms of the Airy line ensemble. So definition. The Airy sheet S from R2 to R2 is the unique in law, I mean, function, continuous function, satisfying 2 properties. So one is sort of just a basic stationarity property. So S is equal in distribution to S of t plus dot for any t in R. And the second property is kind of the key thing, which is how it's related to the Airy line ensemble. So S can be coupled to an Airy line ensemble A, so that, well, the first thing is that if we start at the point 0, then this is just going to be the top curve of the Airy line ensemble. So this is the limiting information which is contained in the Airy line ensemble in the obvious way. Okay, so we get the limit of all last passage values starting at 0. And secondly, for every x in Q plus and y, z in Q, the Airy sheet value from xy, the difference between the xy value and the xz value, is equal to the, but for every x in Q plus y, z in Q, there exists a random k in n such that for k greater than or equal to this random k, we have the following: s of xy minus s of xz is equal to the difference between two Airy line ensemble last passage values. So it's the Airy line ensemble last passage value from xkk up to y minus xkk up to z. So I'll explain what this is with a picture in a second, kind of breaking my convention, because I no longer am doing last passage across a set of n lines. So I need to, I'm always going to be ending at line 1, but I need to specify my starting line now. And here, if you're curious, the value of xk is negative square root k over 2x. So what you have is I draw this Airy line ensemble, the difference between these two last passage values is the difference between, or the difference between these two Airy sheet values, I should say, is the difference between two last passage values in A from a point xk, from a time xk at line k, going up to line 1. So this is when if I go back up here, this star is what you're going to be able to take as xk comma k. And the point is, even though the location on the last passage path in the Milind was random, it was always close to xkk, to the point where you can say, okay, the difference between these two things by this coalescence idea, the difference between the two last passage values from xkk up to these 2 points is the same as the difference between the two last passage values from xn to the minus 1/3 all the way down at line n. All right, so that's all I wanted to say. I'll stop there for questions.
Okay, thank you, Duncan. Let's see, so do we unmute all or somebody? Okay, so I guess anybody who wants to at this point can chime in with a question or comment or whatever. We have some time.
So I have a question. Like in the paper, you also mentioned this Airy sheet have some symmetric property like sxy equals syx as the function. So like, is there any like intuition behind that? I mean, like,
yes.
Yeah.
So this is, I can explain what happens here. This is easier to see with a different model than Brownian last passage percolation. It's kind of not immediate from the Brownian limit. So let me say why this is true. So I'm going to work with Poisson last passage percolation because it's a bit easier. So with Poisson last passage percolation, I imagine in the way that I'm going to set it up, I'm imagining I'm going from sort of time equals 0 to a large time t, which is going to be sent to infinity. And I have a Poisson process here. And then I'm optimizing over all, I'm optimizing over how many points I can pick up along this path from here to here, with the condition that this path should be one Lipschitz, something like this. And so now this pre-limit has more symmetries. So let's try and, I think the easy way to do it is you can always write S of xy equals, so the one that's obvious from Brownian last passage percolation is that S of xy is equal to S of negative y negative x, and then you can in turn write this as S of yx. So the flip symmetry in this Poisson picture is here. These are equalities in distribution. This second thing, which is the flip symmetry, so flipping the sign of both x and y is clear in this picture, because if you flip the entire thing, this is just reflecting your Poisson process across the vertical axis, so it doesn't change in distribution. This S of xy equals S of negative y negative x. If you want to see this in the Brownian, this can even be seen in the Brownian case. So this is just time reversal of Brownian motion. So I'm moving x over here, and I move my point y over here. And if I just flip my Brownian motions around this point, I get the time reversal, which gives me that S of xy is equal to S of negative y negative x.
Duncan, don't you also have the other symmetry, the time reversal in the Brownian LPP, just by flipping the Brownian motions around in some form?
This second symmetry is more involved. This second symmetry, if you want this in the Brownian LPP, this sort of doesn't follow immediately. The issue is if you think of like the RSK bijection, which is going to give you the two tableaux. So if you're working with matrices, it gives you two tableaux which are symmetric, and if you're working with Brownian motions, you get one Gelfand-Sutton pattern, and you get one Gelfand-Sutton pattern, and you get one Milind process, sort of a continuous Gelfand-Sutton pattern like object. And these two things aren't the same, and because we took the limit from diff, and so that there's not an exact symmetry in the pre-limit in the Brownian case. Does that make sense?
But if you just think of it in terms of paths and optimizing, if you flip the Brownian motions so that 1 and n flip and vice versa.
Yeah, that gives you this first symmetry.
Okay,
yeah, that gives you the first symmetry. So the second symmetry it involves this.
But the second symmetry, you can't just flip around the other axis in some way?
Yeah, the second symmetry, you can't easily flip around an axis, yeah. The second symmetry, if you flip it around, you get two things which are equivalent to the limit in the Brownian case, but they're not equivalent in the pre-limit. They're equivalent in the pre-limit in basically every other case, except just not the Brownian one.
I see. Thanks.
Other questions for Duncan?
May I ask a question?
Yeah, of course.
I have two questions. So the Airy sheet is a scaling limit for the last passage percolation value. So do you have any more information on the behavior of geodesics?
Yeah, so I sort of, because given the length of the talk, I kind of just focused on this. But yeah, we can get, so the Airy sheet, if I draw the picture, the Airy sheet is the scaling limit when I fix my line n and 1. So the Airy sheet tells you all last passage values between these two times. What you can do with the Airy sheet is you can build up the scaling limit of all last passage values when you're allowed to vary both of these times as well. Okay, and then this gives you then this gives you a limiting random field, which gives you distances between any pair of points in the plane which are ordered in the time direction. So this is sort of my time direction this way. Okay, so this is the directed landscape. And then you can, okay, you have a notion of distance between any two pairs of points. So you can say what a geodesic is in this setting. So a geodesic is just going to be a path between, maybe I wasn't intending to erase there. A geodesic between a pair of points is just going to be a path where if you subdivide that path into any number of segments, then the sum of the distances here is equal to the distance between the two endpoints. Okay. So that's just like if you take a straight line in Euclidean space, you divide it up into any number of points, you just sum the distances along that line, you get the distance between the two endpoints. And when you define geodesics in this way, then basically deterministically, once you know convergence to the directed landscape, you also get convergence of last passage geodesics to these geodesics defined in this way.
And do you have any idea? So the geodesic should be a kind of random processes?
Yeah, so that you can think of, I sort of just fix a few points, so I'll just fix, you can say go from time 0 to time 1. A geodesic is going to be a random function from 0, 1 to r, satisfying in this case pi of 0 equals 0 and pi of 1 equals 0, the way that I've drawn it. I'm sort of drawing my graphs in a funny way. And then sort of exploring the structure of these is work in progress, but what's proven in this paper is that these are sort of Holder almost two-thirds, so they're a little bit, they're more regular than Brownian motion, for example. Yeah, did you have any more particular questions about geodesics? I might be able to say more.
So maybe actually in this spirit of trying to say roughly on schedule, maybe we should all thank Duncan for a very nice talk. And we're going to take, let's say, a 3-minute break. So we'll start up at, well, in my time, 12:53, but you can work it out for yourself with the next talk, which will be by Milind. So in the meanwhile, Milind, why don't you set up your screen?
I can stop sharing.
So with that said, so it's a pleasure now. Now we'll have 3 shorter talks, about 20 minutes with questions. The first pair will actually be a joint work between Jake, Milind, and Alan Hammond. And Jake and then Milind will speak about that. So we'll start with Jake.
Well, thanks everyone for joining, and thank you to the organizers for the invitation to speak about this work. The new results I'll mention are all joint work with Alan and Milind, and as Ivan was just saying, Milind is going to speak immediately after this talk, and while I'll be discussing the main result of our recent work, Milind will be going into some of the details of the proof, the main idea of the proof. And he's got a lot of nice figures, so you should stick around for that. And part of the reason I'm excited to talk to you about this today is that it fits in really nicely with the lectures that Ivan gave earlier this week, in particular the second one. And it's also because one of the results he covered is, I think our work is something of a sequel to it, in a very natural way that I'll talk about. Okay, so our path to discussing the main result is by asking what is meant by quantitatively Brownian nature. But in order for you to care about the answer to that question, I should say a few things about the Airy 2 process and the Airy line ensemble as motivation. So the Airy 2 process is worth studying in part because of its association with the KPZ universality class. So there are models of interfaces, either directly modeling interfaces or models that can be associated to interfaces. And these are interfaces which are arising from a particular kind of growth. And perhaps after subtracting off some drift from these interfaces, after some characteristic rescaling that is characteristic of the KPZ universality class, and in the limit of advanced time, in some cases it's proved, but in other cases it's just expected that those interfaces converge in distribution to the Airy 2 process shifted by a parabola. So this thing has some global curvature because the Airy 2 process is stationary. It's globally parabolic, and we'll see an image of that in a second. But I just want to say that some of these models to have in mind are like, for example, the narrow wedge solution of the KPZ equation, TASEP, Brownian last passage percolation, and there are many other examples. So the point is that the Airy 2 processes we're studying because of the connections to these models. And if you learn something new about the Airy 2 process, it can have ramifications for these other models. But if the Airy 2 process is the thing that you care about, then why is it even worth talking about this whole ensemble of curves? As a note, the Airy 2 process can be embedded as the top curve of the Airy line ensemble. And what's depicted here is not the Airy line ensemble, but a parabolically shifted version of it. And that's so that this top curve is this limiting scaled description of the interfaces arising from certain growth models. Here are just depicted 3 curves, not all of them. But the reason for embedding the Airy 2 process into a line ensemble, even if you're just interested in the Airy 2 process, is because the line ensemble has, the one that's depicted has the non-intersecting Brownian-Gibbs property. And in its simplest form, this means, for example, that you could take the top curve in this ensemble, erase it on a particular interval, sample a Brownian bridge that matches the endpoints, and so long as it doesn't intersect the curves around it, that whole procedure has not changed the distribution of the ensemble. So by embedding it in this ensemble, you get a new tool, not only to study the other curves in the ensemble, but in particular to study the Airy 2 process. And of course, there are other reasons to study the Airy line ensemble, and Duncan was just talking about some of those. It has connections to these other objects of importance, like the Airy sheet in directed landscape. But getting back to the Airy 2 process, what does it look like after we've shifted it by a parabola? Well, of course, it has this global parabolic curvature, but the thing that we're going to focus on is the fact that it's locally Brownian. And there can be many senses in which the Airy 2 process and this parabolically shifted version are locally Brownian. And local indicating that we're looking at a particular interval. And then if you wanted to try to phrase locally Brownian, how would you do it? Well, if you were looking at this curve, you might think, well, I'd like to compare with Brownian motion, started from this same time here. So maybe instead of looking at the curve on the interval, I should look at its increment. And that's what we'll do. We'll compare the increment of this curve over an interval with Brownian motion started at the left endpoint of that same interval. But to set the interval, we need a parameter d. D is going to determine the length of this interval that we're looking at. And to more briefly talk about this Airy 2 process minus a parabola, we'll write it as L. The Airy 2 process is locally of rate 2, whereas Brownian motion is of rate 1. So in order to compare them more easily, we just scale down by a factor of this 2 to the minus 1/2 here. In that way, comparing L and Brownian motion is easier. So here's the first sense in which now L is locally Brownian. This is a result that Ivan and Alan proved in 2014. And here's what it says. The law of the increment of L is absolutely continuous with respect to Brownian motion. So this result is generally interesting because it's providing the sense in which L is locally Brownian, a new sense in which it's locally Brownian, but also because it's useful. Getting estimates of the law of L can be challenging, And because it's such an important object, you would like to obtain those estimates. In this particular case, if your estimate of that result or if your estimate for Brownian motion for the corresponding event is 0, then this result can transfer that estimate to the law of L. And that's just by the definition of absolute continuity. And here's a nice application. At the time this result came out, there had been a conjecture that stood for about 10 years that said that L attains its maximum at a unique location. And this result on absolute continuity proves it in short order. And that's because on any interval, Brownian motion will take its maximum at a unique location almost surely. And so in a sense, what this result does for you is that if you have some 0 probability event for Brownian motion, it gives you that same thing for the law of L. And just a leading question, it's natural to ask, well, can you do the same thing with events of a probability that is say epsilon? And of course, I'm saying this because the answer is yes, and I'll tell you about that in a second. But I think the quickest way there is to clear off these comments and rewrite absolute continuity in terms of its epsilon delta characterization. And so here's a characterization of absolute continuity. If you give me a delta, then I can find you an epsilon such that if A has Brownian motion probability less than epsilon, then that means that for the law of the increment of L for the same event, it has probability less than delta. The thing is that there's no relation specified between epsilon and delta. And this is where our result comes in.
You have a slightly, you have a delta epsilon notion of the traditional role of delta and epsilon, or the other way around in analysis. I suppose it doesn't really matter. Sure.
Yeah, and in this case, we can get rid of delta altogether because in this case, we've sort of quantified their relationship. And the result is that if you have some event A and its Brownian motion probability is at most epsilon, then for the law of the increment of L, it's at most epsilon with some corrective factor. And I'll tell you in a second, I'll show you what the corrective factor is, and you'll understand why I didn't include it on this slide. But first, I want to speak to the general usefulness of this result. And it's aligned with the comments I made about the absolute continuity result. Obtaining estimates about L can be difficult, certainly more difficult than obtaining that same estimate for Brownian motion. And that's sort of the philosophy behind this result. If you want to get an estimate for L, why don't you get it for Brownian motion instead? And then using this result, you can get your corresponding result about L. And in particular, in the context of this absolute continuity result and Johansson's conjecture, whereas originally with the absolute continuity result, you were asking the question, does L take its maximum at a unique location? Using this result, you can quantify that. You can ask how likely is it that there are, say, k near maximizers in a sense. So you can ask more refined questions using this result. And next, I'll say that even though L is just a single curve, in fact, a similar estimate applies to any curve of the parabolically shifted Airy line ensemble. And in fact, it's even of broader scope than that. You can go beyond the Airy line ensemble there. There are other ensembles. For example, you can apply this result to Brownian last passage percolation, although I certainly don't have time to talk about that model. And finally, as promised, here is the form of this corrective factor. So to see that this is actually less than the reciprocal of epsilon, you can imagine that because the reciprocal of epsilon is say something large, after you take its log, it's still something large. And then instead of having the 5/6 power, you can just raise it to the power of 1, drop the constants, and the thing you get out is 1 over epsilon. So that shows that indeed this is a corrective factor and not the leading factor. Okay. So to conclude, I mentioned this version of Johansson's conjecture where you quantify it. The corresponding result for Brownian motion takes a little bit more time to prove. And so we've chosen for you a nice sample of how you could use this main theorem. So here's a tail bound on the supremum of the increment of L over an interval. And the same quantity has been bounded before in the literature, but instead of x squared over 4d being this first term here, there's an unknown constant c, and instead of 2, it's 3/2. So this is really the leading order term you'd like to get, and we can get it, and it's precisely because it's the term that you would expect for Brownian motion. The main result tells you how you should go about getting this bound. You should do it by simply considering the same thing for Brownian motion. And so as opposed to considering the increment of L at S, you can consider Brownian motion at S, where that Brownian motion is started at -d. And by the reflection principle, you know that the supremum of Brownian motion over an interval can be related to Brownian motion at the end of that interval. And Brownian motion at the end of this interval of length 2d is just a normal random variable with variance 2d. And so in the language of our main result, you'll want to set epsilon to be some constant times this e to the minus x squared over 4d because the length of the interval is 2d. And that's basically it, because all that's left to do is then identify this corrective factor. It has this form. So you plug in epsilon, and this is the correction you get. And so you plug that in, and you're done. So this is an illustration of the usefulness of this result. And there are many other examples that you can find in our paper. Okay. So just as a recap, you care about A and L. Sometimes it's difficult to estimate their laws directly. So instead, why don't you do it with Brownian motion? Thanks.
Okay, thank you, Jake. So we're going to pick up with the second part of this talk, which is by Milind. Take it away.
Okay, yeah, so as Jacob already said, I'll be talking more about some of the basic ideas of the proof. So again, just to restate the theorem, we have this subpolynomial error in the estimate for the probability of L, where epsilon is the probability of the same event for Brownian motion. So I won't be going into the main details. It's too complicated for a short talk. But I'll be talking about some of the framework in which the proof operates, which was actually introduced in an earlier paper of Allen, and we build on that to get the result in this paper. So many of the ideas are already present in the earlier paper, but this is what I can focus on. So the basic step is to find a process whose nature is somehow in between that of L and that of Brownian motion. So Brownian motion you understand really well, and L is very hard to understand. So you want something which you can understand, but still is comparable to L. And we prove the estimate for J using the Brownian-Gibbs property. And in fact, J is constructed kind of using the Brownian-Gibbs property. Once you've got the estimate for J, you can then transfer it back to L using some of these earlier results of Allen that I just mentioned. So this is the broad idea. And now I'll be talking about the Brownian-Gibbs property to remind you and therefore describe what J approximately is. So as Jacob said, we embed L in a system of infinite system of non-intersecting curves, which has this Brownian-Gibbs property. And what that means is, so here I've got on the right-hand side, I've got these figures. So you see, suppose you kind of erase the gray part of the first in the first panel between the dotted lines, and you ask for a distribution given everything else in black. And the Brownian-Gibbs property says that the distribution of the gray part is exactly a Brownian bridge between the endpoints conditioned to intersect the lower curve. So that's what the Brownian-Gibbs property is, but I'm going to kind of give you a reformulation or a different way of thinking about it, which will help us get to what J is going to be. So you can think of this unconditioned Brownian bridge as a candidate process. And it has to pass, for it to become what we want it to become, namely L, it has to pass a test. And the test is just what we said before, it's non-intersection with the lower curve. And if it passes this test, it gets the right distribution. And if it doesn't pass, we just try to find a different candidate which will pass. So we keep resampling these Brownian bridges and waiting for it to pass the test. And once it has passed, we have the right distribution. So obviously, the effectiveness of the candidate is going to depend upon how well it passes the test. And by how well, I mean, what is the probability of it passing the test? So if you were in Ivan's course, he calls this, I think, the accept reject probability. So it's kind of a similar idea of passing the test. Unfortunately, the Brownian bridge candidate, the unconditioned Brownian bridge candidate, is not very good, or it's very difficult to get it to pass the test. And there are basically two issues. You have no control over this lower curve, so it could do anything, and you have to be able to pass the test kind of well, no matter what it does. So there are two problems. One is if the lower curve is really close to the upper curve. And in that case, you have a hard time passing the test because you want to touch the lower curve very soon as you start because it's so close. And the second problem is if the lower curve has this kind of internal peak in the middle of the interval, because then the Brownian bridge has to do this kind of big jump to get over the peak in order to pass the test. And so you'll see that the candidate J, which we're going to describe, is going to kind of have features which allow it to overcome both these difficulties with a higher probability. And the way we handle these difficulties with the candidate is that we change the candidate, right? That's what J is going to do. But also more generally, depending on the problem you want to, depending on the problem or the event you want to estimate, you can come up with different. Our main theorem, J, is a useful candidate, but it could not be, it might not be the one for all situations. So the broader philosophy is that depending on the problem, you can decide what candidate to take to be best suited for that problem. And the way to get these different candidates is to choose what data you condition on. So if you think about it, the Brownian bridge, the candidate had no conditioning. It just had the right endpoints, and then you hoped that it jumped over everything you need to jump over. So there was no conditioning at all in that candidate. So you can provide data to the candidate to make it better the final goal of jumping over everything below. And so you can decide how much data to give to the candidate for it to be able to pass the test well. So there are two things you can do. You can give it more data, or you can give it less data. The more data you give, the less Brownian it becomes in a kind of a vague sense. And that makes it hard to analyze. But the less data you give, the harder it is for it to pass the test. And so you've kind of achieved this balance between giving it a certain amount of data so it can both pass the test and at the same time be analyzable without too much difficulty. And that's what I meant earlier when I said J is kind of a midway processor. It's somehow in between L and Brownian motion. So now let's look at some of the things we do in order to make J pass these problems. So, like I said, it has to pass non-intersection near the boundary when it's very close, and it has to avoid internal peaks. So here I've drawn you a sample second curve, which has both these problems at the same time. And to handle the first problem, we use the fact that before we did anything, the top curve of the L ensemble was already avoiding the bottom curve. Right? It was already doing the right thing to avoid the bottom curve. So if we can make use of that kind of knowledge it already has, that will help us pass the test later. So what we do is we take the form of that path and save it for later. So you see, I've just taken the thing at the side, and I've kind of finally shifted it to get the thing on the top over here. And that's how we're going to use the form a little bit later. And the second thing we do is we want to have some idea of where this peak is and how high it is. so that we can then try to jump over it more easily before we have to pass the final test. And to do that, we coarse grain the lower curve and then just save its height at one particular point as a kind of a pole, like a physical pole over which you have to jump. And that's this red line I've drawn over here. And with these two things, we can construct our jump ensemble candidate. So let me tell you what that is now. So first we take a Brownian bridge and just make it go from between the two X's I've drawn and condition a jump over the red pole. So notice that it can intersect the lower curve as long as it jumps over the red pole. That's all it has to do. And you can see over here that in fact, it's not passing the non-intersection test because it's intersecting the lower curve on the left side. And this is where we use the forms of the side paths which we saved earlier. And we're going to put these over here and erase this part of the blue curve. So to see that, we're gonna, so you see that we've taken the same thing and put it over here. It has the same form as above, but it's been kind of shifted compared to what it was in the earlier part. And you see that having done this, the side bridge now avoids the lower curve. And now this whole thing, this yellow, blue, yellow put together, is our jump ensemble.
Milind, where did you get
Sorry,
the,
what do you mean you save it? You save part of a motion, like part from the Airy sheet before you do the resampling, or from like a previous sampling? What are you saving it from?
So we started the line ensemble to begin with, right? And then we conditioned on certain things. In that conditioning, I have saved this side path, but without the endpoint value. So the point is that I have forgotten what this thing is, what this point that I'm kind of circling over here is, and I've saved only the form of the path, if that's clear.
So you mean that's just a path conditioned to go from one point in time to the other without touching the lower curve? So that path is sort of fully conditioned on the lower curve?
So you see that we want to, it depends on what you're conditioning on. So you've got this line ensemble to begin with, and this thing, because it's the top curve, already does non-intersection, right? And we want to resample it in a slightly more sophisticated manner than the earlier things. I think maybe the confusion is that earlier I was sampling only in between these dotted lines, and now I've kind of stepped back a bit and I'm sampling kind of throughout this whole interval. But I'm saving part of the information on the side parts and nothing in between. So it's kind of a slightly more sophisticated way of conditioning than the earlier Brownian Gibbs, the pure vanilla Brownian Gibbs that I talked about to begin with. And so this is a path taken from the original line ensemble before doing any resampling. So there's no conditioning involved because it already does the non-intersection by definition.
Okay, so you're changing the path a bit outside the window as well.
Yes, yeah, in a sense. Okay, so yeah, so using this path and putting it back in the way I've indicated, you get this overall candidate path. And this is what is basically, so I've skipped a few technical things about how to pick where this pole is and so on. But this is at the core of it, this is the jump ensemble. Yeah, and I just want to come back to the earlier thing I said is that this is one candidate which worked for us for our main theorem, but for other situations, you maybe want some other candidate which is maybe easier to analyze or maybe it's closer to L's nature or whatever it may be. And so by thinking about what kind of data you want to save, which will help you improve what you need to prove, and considering that candidate. Yeah, so thank you.
okay, thank you, Milind. So we certainly have time for questions. Milind was.
So actually, maybe I'll come back to a question somebody asked Jacob about the types of events which are maybe extreme
Sure.
for the theorem. So the basic point is to find an extreme thing for the theorem, you'd like an event which is big for L but small for B, right? That would kind of give you something that would make this tighter. So because L has this lower curve, which is kind of pushing it up, you would want to look for events which somehow make the curve being higher. Because Brownian motion has nothing pushing it up, but L does have this thing pushing it up. But it's unclear whether what the right extreme event is, and whether you'd get a different exponent of 5/6. In the proof, there are many places where that 5/6 kind of magically is the right thing. So it might be, I don't know. So it's kind of hard to, definitely the proof, I think, cannot be improved very much to improve 5/6. Whether that's an indication of it being natural or not is something that I can't say.
So you explained that there's a sort of two-step process. You compared the L to, I think we called J, and then J to Brownian bridge. So, and what you described is how do you construct J, which kind of has not as much conditioning as the full ensemble, but it's not free. So could you explain just a little bit more of kind of how the logic goes? So you've constructed J, but now where do you get these estimates on the probabilities from?
Right.
How do you
Okay.
compare J to the two neighboring L and B?
Right. That's a little bit hard to say. So basically, the point is, let's look at this blue part here. That's essentially a Brownian bridge. And the nice thing about Brownian motion is that if you condition its endpoint, it's a Brownian bridge from the start point to the endpoint. And that Brownian bridge is independent of the endpoints. So we're going to use this property very crucially in that now using the same kind of property for this blue curve, all we need to kind of analyze is where these endpoints are, how high they are, and their distributions. So it all comes down to understanding the distributions of these endpoints, because we already have the Brownian bridge structure inside to compare to Brownian motion. It's kind of hard to say where the estimates come from, but the main heart of the proof is to understand upper bounds on densities of the endpoints here and here, roughly speaking.
Do you need to get very good control on how big this pole can be?
Yeah. So there's a lot of control over how big the pole can be, how high this. So if you suppose you have one more pole over here, you can have more poles, and you have this kind of affine map from this pole to the other poles. There's a lot of control over how high this blue part can be compared to that affine map. Can it be below? It can be below, but how far below can it be? These are the kind of questions that you have to understand to get the estimates.
Could I jump in with a response maybe to a question Omar asked about, you asked a nice question about what kind of event might be sharp. I mean, I haven't thought very carefully about this, but one thing I think it would be fun to look at is an example. If you take a Brownian example where you swing, you take on a unit interval, and then you begin at 0, and you swing down a long way and back up and end roughly near 0, kind of an event of this type. So if you have a bit of a think about how could you see that kind of behavior up to a vertical shift, so this whole sort of valley object could be moved up and down, and then how could you place that in the parabolic Airy ensemble? Well, you see, you would have a little bit of a problem, because in the parabolic Airy, as the top curve, so the other curves are relatively flat, or they follow the shape of parabolas. Just think of them as being kind of rather fixed. It's very, very difficult to insert structure and to push curves down, because the negative tail of GUE is very, very quickly decaying. So this kind of behavior, if we're going to have it, is going to have to sort of come in at the top. And so if it has a valley coming down, it's an extra challenge, because it necessarily pushes the endpoints rather up high. So you see, the only way you could have it for Airy is to have a more demanding roller coaster ride, where you have to rise up a long way to actually hit the top, so that you can come back down and go back up again and come back down again, and actually have that structure sitting there. So you see, there's an up down movement you have to make within the Airy, whereas in the Brownian you only have to make a down up movement. So you could have a bit of a think about that example, and it would indicate some degree of tension and difference between the objects. Oh, and then there was another good question, I think maybe it came from Ivan, about the KPZ line ensemble and whether these techniques can be adapted. So you see, we have a coarse graining in which, as Milind was saying, we have these poles and kind of saying you have to jump over them. That stuff doesn't work without modification in the KPZ case, because everything is soft. In the KPZ case in Ivan's talk, curves can cross one another. So if I just tell you somehow that there's this pole, well, it's infinitely narrow, so it doesn't actually have any energetic cost to cross it. So it wouldn't be the right formulation. There might be some concept a bit like, you know, a Lebesgue thorn. You know, you would like fatten out the pole a little bit, so it would become energetically painful to cross it. That would be an idea that would be of interest. I think Xuan Wu has been investigating these ideas. There's definitely interesting work to be done to adapt these ideas and get these rather strong moment bounds in the positive temperature setting.
All right, so very nice. So let's all thank Milind. And the third speaker of the short talk session is going to be Erik Bates. Let's see. Erik, spotlight, there we go. Okay. You want to share your screen?
Yeah, I'll do that right now. And then, all right, can everybody see that?
Great. Okay. And so Erik will be telling us about some joint work with Shirshendu and Alan. So take it away.
All right. So thank you very much. Thanks for having me, inviting me to give this talk, and it's a pleasure to be part of this terrific series of talks we've had so far. So I want to kind of jump back to the setting that Duncan had discussed earlier with the Airy sheet. And we're actually going to be going a bit beyond that and talking about the richer object that he had just alluded to at the end in the question session, which was the directed landscape. So what is the directed landscape, just to try to bring us back to speed? So we have this X, Y, and R, and before Duncan was always scaling these, and so the X, Y coordinates were always multiplied by this n to the -1/3 factor. Now here we're actually going to be eliminating that factor altogether. We're just going to imagine we're already in the scaling limit. So before we had some picture like this that we imagined maybe we were going between two fixed times 0 and 1. And it's important to remember that the Airy sheet, just given as its own object, doesn't actually encode here geodesics for this process. So although Duncan was drawing geodesics, those were for the pre-limiting object. And in order to get geodesics for this directed landscape, which now allows this 0 and 1 to vary. So let's say now I can call these times S and T, where now S is strictly less than T. And then we have this directed landscape, which is this 4-parameter object, which is saying I go from space-time point XS to space-time point YT, and this is now some real number. And we call this function that maps this quartet of numbers X, S, Y, T to R, we call that the directed landscape. And it had this nice anti-metric structure, or in fact, this was maybe just alluded to a bit, but let me make it a bit more precise. So for any R that is strictly between S and T, so we have some intermediate time, then the directed landscape obeys the following composition rule. So instead of looking at just fixed points between S and T, I look at this intermediate point R, or immediate time R. And then at time R, I imagine, well, let's look at all of the possible space coordinates. And then imagine, instead of going directly from X to Y, I go X, S first to ZR, and then I continue on my journey from ZR up to YT. Okay. And if I take the supremum over all possible intermediate points Z, so let's say this is the Z that maximizes this sum, then now this isn't telling me somehow how the path, if there is such a thing between X and Y, should act when it hits time R. So you can imagine, instead of just restricting ourselves to a single time, let's further divide up this time interval between S and T. So I have all these intermediate times, and for each one of these intermediate times, I can consider this variational problem of where does the Z that maximizes this functional belong. And maybe it's not unique, but most of the time it will be. And so kind of ignoring some technical details that must be addressed, you can imagine that I maximize at each individual time, and then I compose all of those times together in the limit, and I get some path. And because I've chosen always the maximizer, this path, this gamma, I'm going to call it, is now some geodesic. So to call this geodesic, it means that I'm comparing it to other paths. And so you could imagine that if I gave you some other candidate path, so let's say here's some other candidate path between the two space-time points, I could do this process backwards. I could restrict myself to all of these finite times and take a shorter and shorter separation between the times, and I could construct a limiting weight for said path. So this other candidate path that I've colored here in red, this now may not be a geodesic, and for a generic path, in fact, the limiting value of this procedure would give me -infinity. But if I just go through just constructing the geodesic path, I can imagine just maximizing this composition rule right here. Okay, so we have some way of, for any given path, determining a weight according to the directed landscape. And here I've especially used the fact that I have the weight at any intermediate time. And so this is kind of what distinguishes the directed landscape from the 2-parameter Airy sheet object that Duncan was talking about earlier. And he kind of alluded to how you could take the Airy sheet and from it actually get this richer object. So I'm using this as a starting basis, and just to kind of give us a sense of what other starting facts we can use. So from the paper that Duncan had with Janos and Ballant, we know that geodesics do exist. So there is a probability 1 event such that between any two space-time points, there do exist geodesics. And you can imagine them just as being constructed by this variational property. And for any given pair, x, y, and say I'm fixing my time horizon st, for any given pair, it's almost surely unique. So there's almost surely one geodesic. But we have this limiting scaling object, this L, this directed landscape, and it's supposed to be universal. And so you can imagine that in the same way that we'd like to study fractal properties of, say, Brownian motion, which is another universal object, as Ballant pointed out in the chat earlier, the universal object here for this KPZ universality class, this directed landscape L, this also we want to understand fractal properties of. And so the question, just to get us started, that you might ask to study certain fractal properties of this directed landscape, when does this fail? And maybe how does it fail? And here I'm saying it fails for random points. So for deterministic points, I know that almost surely I have a unique geodesic, and so I have to take a realization of this directed landscape, which you can imagine as it's giving me some random noise environment that I can then construct paths and geodesics from. Okay. So here's the question. And let me just pause for a moment to ask if anybody has questions they want to direct to me. Okay, so let me recopy this picture here. And let's just consider how this question of geodesic uniqueness might fail. So for instance, I have some geodesic between X and Y, and maybe if the geodesic uniqueness fails, maybe at some intermediate times, there's some alternative path that I could take that's equivalent. So from the segment between where they separate and where they join back up, those two have the same path, the same weight rather. And so I have two possible geodesics, and say they're the leftmost and the rightmost geodesics. Well, this kind of picture actually shouldn't really exist. And let me kind of explain why. So if I zoom in, let me take a deterministic point very, very close to y. And then let's go back to a deterministic point very, very close to x. Well, if they're very, very close, then you can imagine that the geodesic between the deterministic point close to y and the one close to x, it should like to first hook up with the geodesic that goes from x to y, because we already know that's a good route to take. And so in fact, for this deterministic pair of points between something close to x and something close to y, once it gets to this key fork, it could take either route. And so in fact, if I had such a picture that I draw with the blue and the red, then you could realize deterministic points that violate this uniqueness condition. And so this is actually not the kind of picture we want to study. So instead, what we want to consider is a picture like the following. So again, I have some geodesic between x and y. And instead of going away at a random time, I'm jumping off, leaping away from the blue geodesic immediately and not returning until I get back to the end. This is the type of picture we want to ask: how frequently does this happen for random points in a typical realization of the directed landscape? And so the theorem that we have, that maybe I won't have too much time to explain how we get there, but the theorem is that if I look at the set of x, y, so I'm looking at a subset of R2, such that this picture happens. So let me copy it here. Do that, paste again. So if I look at this set, then the Hausdorff dimension of this set is equal to 1/2. And so this gives us a fractal quantification of how frequently we observe these disjoint geodesics. And in a way that I won't exactly make precise right now, these exceptional points of geodesics do somehow encode the critical information of the directed landscape, where the action happens, so to speak. Okay. So it's just a simple statement about the size of this set, and this holds almost surely on the realization of the directed landscape, this random object. Okay. And let me also give you another way of seeing this result. So there's also what we might call a univariate version of this. So let me draw, again, this picture. But now instead of taking just a single point x at the bottom, let's take a second point. So we'll call them x1 and x2. And a typical way that I observe geodesics, say from x1 to y, and then another geodesic between x2 and y, is the following: that eventually the geodesics will hook up before reaching y, strictly before reaching y. And so the exceptional picture here is, instead having this, I have, again, the same geodesic between x1 and y, but now I'm going to have a geodesic between x2 and y that only reaches the geodesic, the first one, exactly at the point y. So this would be an exceptional behavior. So here again, it's important to realize what I'm fixing. So before I was fixing the time horizon s and t and allowing x and y to vary. Now I'm still fixing the time horizon s and t, but now I'm allowing y to vary, only y. I have fixed my x1 and x2. And so if you fix x1 and x2 for a typical y, the geodesics between the 2 points in below and the single point above will coalesce prior to reaching y. But there will be exceptional y for which I have the picture on the right, that I have some exceptional circumstances under the geodesics that they coalesce only exactly when meeting y. And so for this type of setting, we again have a Hausdorff dimension result. So again, let's say we have, now this is a univariate version. So I look at the set of y in R such that I have this type of picture. This over. then the Hausdorff dimension of this set is again 1/2 almost surely on the realization of the directed landscape. Okay. And these two are very much related. So in fact, there is some way of deducing part of the first result from the second result. And I won't necessarily go into that. I want to just spend maybe the last few minutes here explaining where this 1/2 comes from, at least say in an upper bound sense. And this will kind of get into just the very beginnings of what methods we're using here. So the directed landscape, as Duncan mentioned, was coming from this pre-limiting object of Brownian last passage percolation. And for this pre-limiting model, we have a lot of useful estimates. And one such estimate is the following. So here I'm imagining the analogous picture in the directed landscape. So let's again draw some time horizon S and T. And then the event that I want to consider, so now I'm imagining something in the pre-limiting setting, but it's still in a scaled picture. The event that I want to consider is that on some deterministic windows above and below, on the top and the bottom of width epsilon, the probability that there exists disjoint geodesics between some two pairs of points, beginning and ending in those intervals, this is asymptotically upper bounded as epsilon tends to 0 by epsilon to 3/2. Okay, and there's actually a generalization of this, and this is in work of Allen. So this is in the paper of the Proceedings of the London Math Society. Okay. So there's actually a generalization of this to k disjoint paths, where the 3 exponent there is replaced by k squared minus 1/2. So the 3/2 in the case k equals 2. And what this gives you is, now imagine that I'm looking back at this type of picture right here. Well, in the pre-limiting setting, you should imagine that I'm taking this sort of picture, but now I'm allowed to vary the top and the bottom. So you have some entropy factor. So you have, on a unit order interval, you have epsilon to the -1 windows you could take upstairs, epsilon to the -1 windows you could take downstairs. And then you multiply that by the probability that's tending to 0 of epsilon to 3/2, and you're left with epsilon to the -1/2. And this 1/2 is exactly where you should imagine this Hausdorff dimension of 1/2 coming from, at least for this result. And this is actually obtained in a similar way, but you have an intermediate step because you're only varying the point upstairs. So this just gives you some of the sense of how the pre-limiting objects and the limiting object are interacting. And there's a back and forth, and the importance of studying these sorts of questions relates exactly to that back and forth, because we think the directed landscape should be a limiting object. So with that, I'll stop here and ask for questions. Thank you.
Okay, thank you very much, Eric. So we can. Okay, people need to unmute themselves to clap. So we have time for a few questions, if there are some. And then after this, we'll take a little break before Shirshendu's talk. Is there a sense, so you're looking at Hausdorff dimension. Is there any sense in which you can kind of, if you're looking at something that's of dimension 2 in R2, you can talk about the actual area of it, right? So it's a Hausdorff dimension 2, but it has maybe an area associated to it. Is there some sort of secondary measure on top of the Hausdorff dimension, something that will be random, that you can quantify or understand for these settings?
Yes, so there is an underlying measure that we're interested in, and that's exactly the measure. So let me explain that maybe just momentarily in the one variate setting. So referring back to this result here, you could imagine that there's
you might need to share your screen again if you want.
Okay, yeah. Let's go back. Well, maybe I'll kind of say it in words. So you have those two bottom points, the x1 and the y, and you have the top point, the x1 and x2, and you have the top point y. And as I vary y, I can compare what's the difference in weights between x2 and y minus the weight between x1 and y. And if I vary y and I look at this difference, then it's a fact that you can check as an exercise that this is a monotonic function, non-decreasing in y. And so this actually encodes a random measure, not a probability measure, but a random measure, random positive measure on the real line. And this difference weight profile is encoding the distribution function for this random measure. And what the result here, actually, the proof of our lower bound, I've kind of given you the heuristic for the upper bound, goes through this measure. And we say that the support of this measure is contained in the set of y, such that you had this disjoint geodesic picture. And so now we're getting a result that says that the Hausdorff dimension of that measure has support 1/2, and it's a Cantor-like measure. And so in this sense, you do have some geometric information that that is being implied by the Hausdorff dimension result of this measure. I don't know if that exactly speaks to your question, Ivan, but there are underlying objects, measure valued objects that we're interested in.
Oh, that's very good. Other questions? Oh, so while we have the awkward pause, so let me just say, so we'll, assuming there are no more questions, then we'll shout them out if there are. We'll start again in 8 minutes at 2 o'clock. In the meantime, let me just encourage people to turn on their videos. I like seeing names, that's always nice, but I like to see videos even more. And it's nice to see people and say hello and all that sort of stuff. So we can imagine that we're almost in person having real interactions. People are responding, wonderful. And then maybe even after Shirshendu's talk, if people want to stay on and chat and just introduce themselves, if you think you need introducing, whatever. Pretend like we're at a conference and you can just walk up to people and say, hi, I'm George and I'm here. Okay. So feel free to do that now or after Shirshendu's talk. Probably not during his talk, but any time would work. All right, so we'll take a little break, but shout out. Okay, a lot of people responded. Wonderful. Now we see faces. How did you think?
Hey.
So hello. I'd like to say something. Not much. My name is Priscilla Greenwood. I'm a probabilist from way back, long before there were any such structures. And but there was Gibbs fields, and I learned about that. And so I'm playing catch up big time with you here. Just delighted to have so much learning so fast. Big learning curve here. So thank you very much.
Oh, very glad that you could join. And you asked a very good question on Tuesday about the applications for KPZ. I don't know if you emailed me. I didn't respond yet.
No, not yet. I thought I'd give you a break for a few days.
Okay, fair enough. Well, yesterday was a day of protest. So there was no work that day, though we certainly thought about things that could be done to help with the situation in the world right now. Actually, if anyone had good ideas from yesterday that they wanted to mention, that's also a nice thing to do now. My wife was suggesting that we have a program for the local Boys and Girls Club. People trying to help them figure out that mathematician is, or STEM is actually something that's attainable. That's a direction that people could actually take. So we might look into that. Who knows? But it's hard to feel like you can really do much in times like this. But I guess every last drop matters. So. Would anyone else like to say hello? I see you, Sean.
Maybe I can just add that
Great.
one of the participants, Giorgio Cocomelo, put up a list of both reading material and suggestions for potential activities for yesterday and then going forward from yesterday on the Zulip. So the sort of discussion forum for OOPS. There's a link to the Zulip on the OOPS webpage if you don't already have an account for you to sign up. And you can find that in the general stream under the title BLM and Strike for Black Lives. So thanks to Giorgio for putting that together.
Are the streams of, is there a link that we can just send in the chat for people? All right. Oh, I see. Oh, there's a bunch of stuff. Okay. Yeah. Oh, here, I can try to copy it.
I've just done that.
Oh, the chat doesn't allow you to write that much, but yeah. Wonderful. It's nice to see people who I haven't met in person on here and to look forward to actually being able to meet people in person at some point. Hey, Shirshendu.
Yeah, Evan.
All right, so you'll, in a minute or two, we can switch to your slides.
Yeah.
And you'll go, let's see, 40 minutes and then.
Yeah. So I guess Milind will be, I'm usually sort of used to looking at the window when I'm speaking because I've done some remote teaching, but I guess Milind will probably be officially sort of looking at it and then maybe pointing me to.
Okay, that sounds good, yeah. Okay, so let's see. So the other people who have videos, let's see. So I see Sarah Hernandez Torres. Hi, Sarah. Where are you coming from?
Oh, I'm in Vancouver.
Vancouver.
I can tell that you are not missing much because it's raining and it will
Oh, yeah, okay.
for the next 10 days or so.
Well, yeah, I guess that's probably, maybe in 2 years it won't be raining. I haven't looked at the forecast, but.
Yeah, I think Thursday is going to be sunny and then it will continue raining again.
Oh, okay. Well, so then we lucked out.
I'm very glad to see you all.
Yes. Okay, and I see Schwan. Schwan, is that a backdrop? Is that a fake screen behind you? Yeah, okay. And I see Peter Nair. Nice to see you. Okay, and Jake and Eric, Milind. Hi, Andre. And Thomas, one of the organizers. Sendar, I don't think we've met. Nice to meet you. Where are you coming from? Okay.
Is that Serdar?
Yeah.
Oh, hey.
Or
Yeah.
Sardar, sorry.
I'm from UBC.
Oh, you're UBC. Okay.
Yes.
All your random samples seem to be UBC people.
You know, it seems like I should go and visit there sometime. I haven't been for a few years. Okay, and then Ling Fu, nice to see you.
Well, you don't have to wait for 2022.
Yeah, right. All right. Yeah, we'll see if they allow travel before then. And Hugo and Ji Peng, nice to see you. And Ofer, we've emailed. I don't think we've met in person. So, hi, Hindi. Okay, I see Ed and Pramit, my student, and Shirshendu. And Evan, I've seen you on other chats. I don't think we've met in person though. You're at Wisconsin, right?
Yes.
Okay. Oh, and hi, Leo. And Roger, hi, nice to see you. And Farad, where are you coming from?
Oh, hello. I'm actually in Europe right now. So
okay.
I'm coming from Grenoble, France.
From Grenoble. Okay.
Forêt, yeah.
So I found somebody who's not at UBC.
Yeah, finally.
Well, very glad you joined us. Okay. So I think the time has come that we'll transition now to Shirshendu's talk. Let me spotlight him. Okay, Shirshendu, do you want to?
Yeah, let me do that.
Slides?
So we are recording once again.
Wonderful. And let me encourage that after the talk, people stay around and show their video, and we can, you know, say hello, and it's just a lot more fun that way. Okay, so Shirshendu will speak to us about watermelons, which sounds quite good right now, and joint work.
I just wanted to check, is the whole slide visible? Like,
I can see to the bottom of 2 boxes.
can you see this?
I can see that just at the bottom edge.
Yes.
Okay. So take it away, Shirshendu.
Yep. All right, good. So yeah, thanks again for the organizers, to the organizers for this invitation and really nice series of talks. So what I'll talk about today is some recent results about objects known as geodesic watermelons. I'll define what these are, and everything in this talk is going to be based on joint work with Riddhi Basu, Alan Hammond, and Milind. I guess all of them are here. And I think Milind will sort of navigate the chat, so feel free to ask questions. And also you can, I'm not sure if this is allowed, but you can also sort of unmute yourself during the talk and ask questions. Okay. So just to sort of get things started, so we'll work with the lattice last passage percolation model. So this is sort of an instance of a sort of box in Z2. So every vortex, so the picture is really about the dual lattice, but every vortex in Z2 actually has an ID random variable. XV will be the vortex, the random variable attached to the vortex V. And just for concreteness, I'll sort of start with sort of assuming all of them are ID exponential with rate 1. Although the arguments are pretty robust, but let's, for concreteness, take this to be the starting point. And then we have heard the word geodesic a lot of time, just to sort of again set the stage. So the geodesic for us would be, so you'll start from, let's say 1, 1, and then go up to NN, and it's going to be an oriented upright path, and such that the weight it accumulates, which is the sum of the random variables along that path, is maximized. And like I said, so this is the starting point, but the arguments really will not really use any precise details of this distribution. Okay, so again, some notation. So xn is going to be the geodesic weight from between 1, 1 and nn, and gamma n is going to be the unique geodesic. So this is sort of the random variables are continuous, so no 2 paths of the same weight. So there's going to be a unique path which maximizes the weight. So that's going to be called gamma n. And again, so a lot of stuff is actually known for this exponential model. So it's known that the law of large numbers for this random variable xn is 4. So it's typically like 4n, and then there are some fluctuations. And the fluctuations are given by this kp's exponent 1/3. So more precisely, the scaling limit of this random variable is something which is an order 1 distribution. So xn minus 4n, and then you have to scale by n to the 1/3. There's a constant floating around, which is not too important. And the limiting distribution is what is known as the Tracy-Widom GUE distribution. So I'll not again talk too much about it, but one sort of important fact for us would be that the mean of this distribution is negative, which means actually xn for any finite n, the mean of xn is actually strictly smaller than 4n, and it's actually going to be 4n minus some constant times n to the 1/3. And actually much more is known. You actually do know a lot of strong tail bounds for this random variable xn, and also large deviation bounds. And so these go back to work of Johansson, and then subsequently via the random matrix connections, work of Ledoux and Ryder. So a lot of stuff is known about the tail properties of this random variable xn. Okay, but then there's also another geometric object lurking behind, which is the geodesic itself. And so you can also talk about fluctuation properties for the geodesic. And so one particular observable of interest is, so you start from 1, 1 and you go up to nn, and then one natural question is, how much does it sort of move off the diagonal by? So we know if this was a Brownian bridge and this box has size n, then this would be typically root n, but it turns out here it's the other kp's exponent shows up, and the maximum deviation you expect from the diagonal of this random path is roughly of the order of n to the 2/3. And again, you have sort of quantified versions of this. So TF is going to be my notation for the transversal fluctuation, which is, I won't define it precisely, but it's going to be the maximum that you deviate from the straight line. And so a tail bound like this is true. So transversal fluctuation being bigger than x times 10 to the 2/3 has a stretch exponential e power minus x cube type tail. And so like this was so some sort of not optimal, but tail conditions were proven already in this paper of Reddy Basu, Alan Sly, and Vladas Siderovicius on the slow bond problem. And then subsequently sort of adapting these arguments, one can actually get the optimal exponents. Okay, so we're talking about the geodesic from 1, to NN, but you could also sort of vary the endpoints. Instead of taking NN, you can vary them along the straight line x plus y equal to 2n. So this is, let's see, I can probably highlight it. So is this marker visible? So
yes.
Okay, so this is sort of the straight line x plus y equal to 2n, and so NN is the center point here, and so you're talking about geodesics going from 0, 0 to NN, but you can also sort of talk about geodesics going wherever. And so it turns out that there is a process version of this, which again has been alluded to in many of the previous talks. So just to sort of again set up the notation. So suppose you take any point, this red point on this line, and let's say it's sort of moved away from the diagonal point NN by some n to the 2/3 type scale. So this is, let's say, n minus n to the 2/3 x, comma n plus n to the 2/3 x. So it turns out that if you look at this entire process and again have the same centering and scaling, you get a process convergence, and the limiting object is this. So there is some concavity going on by superadditivity. So this is this minus x squared term. And then of course you have the stationary Airy 2 process that gives you the fluctuations. So as a result of this parabolic loss that you get if you go away from the center point, it turns out you can prove that if you take any path from 1, to NN with transversal fluctuation actually bigger than x times n to the 2/3, typically the weight loss that you see from the typical value of the geodesic is going to be x squared times n to the 1/3. So n to the 1/3 is this fluctuation exponent, so that's always going to stay there, and so the dependence on x is parabolic. Okay, so typically things that are far away from the diagonal by x times n to the 2/3 suffer some quadratic loss in x. Okay, and again, so we have already seen this line ensemble before. So this is sort of the top curve. This, if you plot this Airy 2 minus this x square object, this is what it roughly looks like. And this is the limiting scaled weight of the geodesic. But again, as we have seen, you can actually embed it in a line ensemble. And I guess I should have said parabolically shifted. So, but it is actually a part of a bigger line ensemble. And it turns out that the other curves in the line ensemble also have some really nice sort of geometric interpretation. It turns out the following thing is true, and this is really going to be the sort of starting point leading into the definition of what geodesic watermelons are. So the top curve gave you the weight of the geodesic. Now, if you look at the top k curves and if you sum them up, that's going to be in some limiting sense the weight of the maximum weight of k disjoint paths that you can get, let's say from 1, to NN, so that the total weight is maximized. So you want disjoint paths. They can't all start at 1, and NN because then they won't be disjoint. But you can sort of imagine in a continuum setting, maybe they do. In the discrete setting, you have to do something at the end. But roughly, you have k paths going from the bottom corner to the top corner of this box, so that cumulatively they pick up the maximum amount of weight. So is this statement clear? What the basic object I'm referring to is? Okay, and so just some more motivation. So the line ensemble that we just saw enjoys a resampling property, which was sort of the key in many of the previous talks. And as we have already witnessed, it has been crucial in many of the recent advances. Even in the pre-limit, this maximal weight of k disjoint paths actually sort of exhibit very remarkable connections. One particular would be, so in some of the integrable models, it does actually admit a distributional equality to, let's say, length of top k rows in a random Young diagram via the RSK correspondence. So it turns out that not only do you see this limiting, this k path interpretation coming up in the limit, but also in the pre-limit, there are concrete objects that it sort of is connected to. Okay, so that's one interpretation. It also turns out that this notion of understanding disjoint near optimal or optimal paths, so which also Erik pointed to, like we were looking at the Hausdorff dimension of points admitting disjoint geodesics. But if you also, sort of relax it to be near geodesic or almost a geodesic, it turns out that that's also a very useful thing to understand for many applications. Certainly, naturally, it gives you some understanding into the multiple valleys or the geometry of ground states in the LPP energy landscape, right? So the geodesic itself is a ground state, but typically such landscape actually have multiple valleys, and near ground states or near geodesics are basically these valleys. So understanding these paths actually gives you some insight into this rich landscape. And such an understanding actually has been crucial in many of the recent studies. So like in Erik's talk, so we really sort of, we're trying to really pin down the Hausdorff dimension of such things. In the work of Basu, Hoffman, and Sly, this notion was actually used to understand existence or non-existence of bigeodesics. And also in a more recent work of Alan Sly, Ling-Fu Zhang, and Saurav Sarkar, you can actually sort of transfer understanding of such objects to understanding the kind of effect that a slow bond has in TSF and more quantitative versions of that. And also it turns out there are some nice combinatorial connections, and there's a lot of there's a significant amount of literature in the algorithmic world trying to sort of come up with K best paths, how to compute them efficiently and quickly, what is sort of the running time of such algorithms. So in short, like there are many different sort of places where sort of understanding of such disjoint near geodesics or geodesics actually is quite useful. Okay, so the formal definition. So this is my lattice box. So like I said, so you cannot sort of all start and end at 1, 1, and n, because then you won't be disjoint. But you do the next best thing. So basically, let's say K is 2 for the moment. So you start around, you look at the 2 best paths, one of which start from 1, 1 and end here. And the other one starts at, I guess, 1, 2 and ends at nn. So you look at the 2 disjoint paths, which cumulatively accumulates the maximum weight. And of course, you can generalize this definition to K. You look at the K points along this line and K points going along this line and tie their ends together. And again, if things are continuous, like the exponential variable is, then there's going to be a unique such collection. Of course, for discrete variables, you can have non-uniqueness, and I'll sort of mention some aspects of that maybe towards the end. And the notation would be, so this is a planar picture. So there is a natural planar ordering among the paths. So gamma n K1, gamma n K2 would be the paths in this K ensemble ordered from left to right. And X and K will be the cumulative weight of this ensemble. Any questions about the definition? Actually, can see the chat window first. Okay, maybe I can. Okay. Actually, can see the chat. Okay. Yeah. So what kind of questions can you ask about this object? So the first question could be, so you have this weight X and K. So we know the weight of a geodesic has all this nice fluctuation behavior. It's all pinned down mostly. What is the fluctuation behavior for X and K? And then, of course, the second obvious question is the geometric one. So we have studied the geodesic where the K equal to 1 case. So can you sort of build a similar understanding for the K geodesic watermelon for K bigger than 1? In particular, remember gamma n K1 was the leftmost path. So how much does that fluctuate? So we know that the geodesic itself fluctuates by roughly order n to the 2/3. What is sort of the fluctuation behavior for the watermelon? Okay. So before going into all that, so I just want to sort of throw at you like a deterministic, nice like property that sort of which holds irrespective of any randomness. So of course you can make sense of geodesic watermelons irrespective of what the random variables are. You can just put in arbitrary weights on the vortices and sort of talk about watermelons. So it turns out that this remarkable fact is true, although the statement itself has almost surely, it has actually nothing to do with the randomness. So you look at the K melon and you look at the K minus 1 melon. So you look at the ensemble of K paths that maximize the weights cumulatively, and you can sort of talk about the same object for K minus 1. So you have two ensemble of paths, and it turns out that they interlace. So you have k paths ordered from left to right on the plane, and k minus 1 paths ordered from left to right on the plane, and it turns out that the paths are sandwiched between each other. This picture is not completely correct because you will have some overlap, but it is at least sort of the k minus 1 set of paths is in the region governed by the k paths. And it turns out this is a deterministic fact. There is no randomness in sort of the proof does not require any randomness. And of course, but if things are discrete, then you might have non-unique set of melons, and then you have to sort of make sense of what it means for interlacing. But the version of this is true irrespective of what the weights are. So is the statement clear about interlacing? Okay. Yeah, actually, this was also happening when I was teaching. I would ask questions, but then would have no idea of what the response was.
Yes, it is clear to me.
Okay, so just to sort of quickly give you an idea of how to prove things. This is going to be a proof by picture, very quick, but just to sort of see what kind of arguments go into this. So let's sort of maybe start with a situation where maybe you don't have interlacing. So here, let's say the red paths are, let's say, the ensemble, the 4 ensemble, like, so this red paths cumulatively maximize the weight of 4 disjoint paths, and let's say the blue ones are the 3 melon, okay? And so clearly this does not interlace because this red curve should be actually on the other side. If interlacing was actually holding this picture. So you can sort of mark such excursions. So this is sort of a witness that you don't have interlacing. So this, this red path actually goes on the other side of this green path. And similarly, you can go along from left to right and you can actually mark such excursions. And it turns out that if you actually swap them, so instead of, so the red path, you can actually sort of swap the red part, which actually violates interlacing, by the green path. And you can sort of come up with 2 new sets of paths. And it turns out that because each of them individually were weight maximizing, you will reach a contradiction. So if you do not have interlacing, you can actually identify places where the interlacing is violated and make some swappings of paths, but it has to be a global move. You cannot just do things locally. And you can end up with 2 new set of paths of size k and k minus 1. And they will actually have at least as much weight. But then by uniqueness, if you're in a continuous setting, that sort of gives you a contradiction because you know that there is a unique set of k melons for every k. So I won't go too much into this, but it turns out that this sort of swapping trick would actually help you show that interlacing cannot be violated. Okay. Okay, so now, so there's this deterministic property interlacing, and then let's go back to the original question that we asked, the fluctuation properties of the watermelon. First talk about the weight and maybe then the transversal fluctuation. So here is, so I want to understand quantities like this, right? So here is a 4 melon and I want to understand how much does it deviate from the straight line by. So let's start with a wild guess. So let's pretend that like it's sort of not a super wild guess as it will turn out. So X and K, which is the thing that we are interested in. So remember, each of the paths or the geodesic itself, the law of large numbers was 4n. So typically you would expect if you take k disjoint paths, you would at least be able to match the law of large numbers part. So the law of large numbers should be 4nk because each of them should roughly be 4n. And then the interesting thing is actually the fluctuation and how it depends on k. So okay, so n to the 1/3 was the fluctuation for k equal to 1 case. So let's pretend that you have an exponent, you have a polynomial prefactor depending on k, which governs the fluctuation in this case. So let's say it's k to the alpha n to the 1/3. And similarly, the transversal fluctuation, which was n to the 2/3 in the k equal to 1 case, let's say it's k to the beta, it has a polynomial prefactor k to the beta for some beta. Okay, now you want to predict what alpha and beta are. Okay, so this is supposed to, let's say, hold for all k. And so in particular, it will, let's say this sort of behavior, k to the alpha and k to the beta holds for k equal to n. But if you have k equal to n, then there is only one choice for the watermelon looks like, right? Because if you want n disjoint paths to go from the left side to the right side, they all have to be this sort of horizontal lines. So it has to basically fill up the whole box. So which means, but now let's say, but the random variables are exponential, so they have mean 1. So if you pick up the entire box, the total weight of the geodesic watermelon for k equal to n would be n squared, not 4n squared. So this law of large numbers term, which is giving you 4n squared, must be corrected by a fluctuation term, which is also of order n squared to get the right thing. Now remember, k is n here. So the alpha, which makes this thing n squared when k is n, is 5/3. And similarly, if you look at the transversal fluctuation, because you know that there are n paths, so the farthest one should be linear in distance, linear in n away from the straight line. This thing should be n, which means if you plug in k equal to n, beta has to be 1/3. Okay, so this sort of naive guess coming from just plugging in k equal to n gives you this prediction. Alpha is 5/3 and beta is 1/3. Okay, any questions? Okay. Okay, so maybe a slightly more informed heuristic rather than just plugging in k equal to n. So we predicted that the fluctuation in space, transversal direction is k to the beta into the 2/3. So suppose you have k paths whose total transversal fluctuation is k to the beta into the 2/3, then the average spacing between each of them is k to the beta minus 1 into the 2/3, right? So the total space is k to the beta. You have k paths lining up, disjoint. So the average spacing allotted to each of them should be on average k to the beta minus 1 times into the 2/3. And also the farthest path, which is k to the beta away, recall that I said that any path that has a lot of transversal fluctuation sort of suffers a quadratic loss in weight. So the path that is farthest away should be suffering a loss of k to the 2 beta into the 1/3 by the quadratic loss that you suffer if you're farther away from the diagonal. Okay, so you have these parallel paths in channels. The farthest one should suffer a loss of size k to the 2 beta times into the 1/3. And so actually, okay, so now you can also do a separate computation. So these paths are assigned some small strip for them to lie in. So this is a situation where you look at geodesics, somehow roughly geodesics, but they're not sort of given the whole space. They're constrained to stay within a parallelogram of some particular width. So you can actually use tail bounds to prove things like if you give me a parallelogram of size n, and the fluctuation on the transversal direction is n to the 2/3, which is the right scaling, but with a prefactor theta, which you should think of as small, then the best path that sort of stays inside the parallelogram suffers a loss, which is theta to the minus 1. You see that this sort of blows up as theta becomes smaller and smaller. Okay, so you can sort of put these two things together. So you have this, so you want to put in theta equal to k to the beta minus 1, which is the average spacing between the paths in a watermelon. And if you do that, and you match the two quadratic loss with the loss suffered because of it being constrained to a parallelogram, you again get the same exponent, beta equal to 1/3. Okay, so there is another sort of way to verify the exponent. Okay, you don't have to sort of parse this too much. The whole point is there are k paths. I give you some total space, so this tells me what the average spacing is. That tells me that individual path roughly is constrained to be in a parallelogram, which means it suffers some weight loss. And then I sort of match that against the quadratic loss that you get because you're moving away from the diagonal. Okay, so here, so given this heuristic, so here is sort of the main result. So the first thing is about the weight. So x and k is the weight. Minus 4nk is the law of large numbers part. So the result is x and k minus 4nk for all k going up to linear in n is typically k to the 5/3 times n to the 1/3. So remember, I told you that the tracy beta mean was negative. So the expectation of the length of a geodesic is actually 4n minus some constant times n to the 1/3. So it turns out that if you amp up k and make k larger, the typical value is actually going to be much smaller than 4nk. It's actually going to be typically 4nk minus some constant times k to the 5/3 times n to the 1/3. So the probability that the weight is actually not like this, so the probability that it does not, the weight does not land in some order 1 window at scale k to the 5/3 n to the 1/3 decays exponentially in k square. Okay, so that's sort of the concentration or rigidity result, concentration result in this case, I guess, for the weight of the watermelon, geodesic watermelon. And then you can talk about the more geometric aspects of it. So about the transversal fluctuation. So
Shirshendu, can I ask a question?
yeah.
So the range that you're dealing with, it gets larger with K, right?
Yeah.
In principle, you would expect that it should get smaller, more and more localized with K, right? Because you're kind of compressing. Or do you really believe that, you know, anything smaller would go to zero?
Actually, I mean, like, okay, so we can go into, so I'll talk about some aspects of this later. So it turns out that you actually, particularly for the exponential case, because you have some connections to other point processes, you actually expect this to be very concentrated. This x and k should be really, really concentrated, much more than, so of course, this bound is sharp in however it's quantified, but you actually expect to have a lot more control on the weight of the geodesic watermelon because of some other connections here.
Mm-hmm. And in particular, when K becomes of order C, this window becomes of order of the limit shape, right? So it kind of doesn't pick up the curvature of the limit shape.
Yeah. Mm-hmm. But the thing that I want to point out is that the probability bound is also sort of improving with K though.
I see. Okay.
But anyhow, so I'll say something at the end which actually will sort of allude to this concentration behavior. Okay, so now the geometric aspects of this. So TF and K, remember, was sort of the maximum that any path in this ensemble deviated from the straight line. So in K equal to 1, we sort of saw it was n to the 2/3, and here we predicted that the polynomial prefactor was K to the 1/3. The transversal fluctuation being bigger than C times K to the 1/3 n to the 2/3 is actually decaying exponentially in K. Now this is sharp just because the geodesic itself has the same probability actually doing the same deviation. So the geodesic typically is n to the 2/3 away from the diagonal, but on some rare event, it can actually fluctuate a lot. And then the fluctuation, the probability that it fluctuates by K to the 1/3 times n to the 2/3 is actually the same. And so it actually turns out that this is a sharp behavior for this object. But the lower tail, so the probability that the transversal fluctuation is much smaller, that everything is super localized near the diagonal. So so you should think of delta as a small number. So the probability that the transversal fluctuation is smaller than delta times K to the 1/3, which means everything is packed in a sort of thin strip along the diagonal, is actually much more unlikely. So it's actually exponentially in K square unlikely. So any questions about the statement? Okay, so I'm actually running out of time. So let me just quickly sort of give you some insight into some of the geometric arguments that go into the proofs. So the key geometric ingredients that we use basically include a specific multi-scale construction of disjoint paths. So we want to understand the best possible K disjoint paths. So to say that it actually picks up enough weight, it actually suffices to sort of by bare hands construct a set of K disjoint paths that actually has reasonable weight. It does turn out that our arguments actually does involve a multi-scale construction of disjoint paths with a weight lower bound. So that actually tells you that the geodesic watermelon actually has weight lower bounded by the weight of this ensemble that we construct.
Oh, I'm so sorry.
Question? Okay, the second thing is the interlacing property that I mentioned. So it turns out that the interlacing property is super useful if you want to prove something for some K. It actually suffices to prove something for, let's say, some nearby J. If you can prove something for some nearby, maybe even random J, then by interlacing, you can actually transfer that knowledge to some statement about a particular K that you want to sort of make a statement about. So interlacing allows you to go between different indices. And the third is a correlation inequality, so this is the Vandenberg-Keston inequality, which has been super useful in percolation, and also recently in this LPP world. It was used in this paper of Basu, Hoffman, and Sly to sort of rule out by geodesics in LPP. So these are sort of the three sort of key geometric things that we will sort of keep using. So I'll probably skip this. So So just to sort of mention what the multi-scale construction is. So the picture sort of at least hints that it's a multi-scale thing. And the statement is you can produce k disjoint paths with total weight, which is at least 4nk minus some constant times k to the 5/3 and to the 1/3, which is the right scaling as we saw in the statement of the theorem, with high probability. So if you can produce such a path, it already sort of tells you that the geodesic watermelon has weight which is at least this. Okay, so that's sort of the construction part. So transversal fluctuation upper bound. Let me sort of quickly give you some insight into the geometric things that go into the proof. So again, recall that any path that moves away from we want to prove that the geodesic watermelon does not deviate too much from the diagonal. This is an upper bound statement for the transversal fluctuation. So recall that any path that moves very far from the diagonal suffers a weight loss, quadratic in how much it moves away y. Okay, so thus an approach to show that the transversal fluctuation is not huge is to show that typically in the watermelon, every path has reasonable weight. So the construction tells you that the watermelon itself cumulatively has reasonable weight. If I want to say that no path actually ventures very far away from the diagonal, it suffices to show that every path in the watermelon actually has reasonable weight with high probability. Because then that would mean that no path actually can have a lot of transversal fluctuation, because that would mean that it would suffer a weight loss, which would contradict a reasonable weight assumption. So this is sort of what I say here. So it's gamma n ki was the ith path in the k ensemble. So if you can show that typically all the paths in the k ensemble actually has this weight lower bound, then you can show that no path actually ventures too much into away from the diagonal. Okay, so we want to lower bound the weight of every path. So it turns out that there is a key inequality which is super simple but very useful, is that the weight of any path in the k ensemble is lower bounded by the weight of the k ensemble minus the weight of the k minus 1 ensemble. Why is that true? You see that suppose you have the k ensemble, right? And let's say I want to lower bound the weight of this path, the green one. If I remove this green one, then I have 3 remaining paths which are disjoint. So the weight of these 3 remaining paths is no more than the weight of the 3 ensemble, right? Because the 3 ensemble is the best possible collection of 3 disjoint paths. So you can use this observation to get this lower bound. That the weight of any path in the k ensemble is lower bounded by this thing, which is just a statement about weights of the full ensemble. And again, by the weight lower bound coming from the construction, you can a priori assume, let's say on a high probability event, that the weight of every ensemble is reasonably large between, let's say, k and 2k. Okay, so this gives you the growth rate for the weight. And so then actually an averaging argument tells you at least that there is some random j in k between k and 2k such that the weight is large for every path in the G ensemble. Right, so you want to use this inequality, which lower bounds the weight of every path by the difference of the weights of the ensembles itself. The weight lower bound tells me that the ensembles have reasonable weight for every j in k and 2k. And this is sort of the growth rate. Then an averaging argument tells you that there is some j which satisfies this nice property, that every path in the ensemble actually has reasonable weight. So which means that I can, because of this transversal fluctuation quadratic loss argument, I can say that this G ensemble is constrained within a strip. It does not fluctuate too much. But remember, I wanted to conclude something about a fixed k, not about a random j. But this random j was between k and 2k. So by interlacing, because of the interlacing that we have already established, if you can prove that any j bigger than k is constrained within the strip, the k melon, which is smaller than j, will also be constrained within the same strip by interlacing. Although the picture here is not interlacing itself, it's just because the interlacing statement is about 2 consecutive melons. And so it can turn out that you can have non-trivial sort of intersections if you differ the index by more than 2. But anyway, is the rough argument clear? So I want to prove a transversal fluctuation upper bound for a particular index. I know weight lower bound for most indices. I want to argue that all the paths are nice. I can do that by an averaging argument. That gives me only the statement for a random j. And then I interlace and then conclude for the fixed k that I was interested in. Okay. Transversal fluctuation lower bound. Okay, so here I want to say that actually it's unlikely that all my paths in the K ensemble is actually constrained in a very thin strip. That's the thing that I want to rule out. So I want to rule out a picture like this. Now recall that paths constrained in thin strips suffer weight loss, which is something that I sort of mentioned earlier, where you look at a path constrained to be in a small parallelogram, thin parallelogram. So actually at this point, and these paths are disjoint. So Weinberg-Keston inequality, for people who are not familiar with this sort of says that if you look at disjoint occurrences of events, if you sort of want to sort of say that two events have occurred, but they have occurred using disjoint parts of the space, then the probability of that happening is actually smaller than the product of the probabilities. So they are it's sort of even more unlikely for that to happen. So using such correlation inequalities, you can actually argue that it's sort of very hard to find key disjoint paths all packed within this thin strip, which all have reasonable weight. Because any given path already, it was unlikely for it to have reasonable weight because it's sort of constrained in a thin parallelogram. And now if you actually sort of want k disjoint copies of that, then it's even more unlikely.
Shirshendu, could you say something more about what this Weinberg-Keston inequality is?
Yeah, so shall we do that at the end of the talk maybe? Okay,
well, I imagine you're getting close to it.
Yeah, so I want to finish something and then maybe we can resume this. Yeah, so, okay, yeah, so the correlation inequality tells you that it's unlikely to find k disjoint paths which are all have reasonable weight. And then we already know by the averaging argument that there is some j, which is now between k by 2 and k, which all have reasonable weight. So the j melon exits this strip. And then again, interlacing tells you that the k melon must also exit the strip. So the moral of the story is you want to prove something for k, you prove something for a random j by some averaging, and then use interlacing. Okay, and so sort of really towards the end, so this is sort of more related to what Ivan was mentioning before about concentration. So it turns out that this watermelon, geodesic watermelon weights are actually associated to a natural point process. So let's say y and k is the difference of the two melons. So x and k minus x and k minus 1. And so then of course you can look at yn1, yn2, yn. So that's an n point process if the system size is n. So it turns out that for integrable models of LPP, in particular for exponential LPP, these have connections to various nice objects. In particular, for this particular case, it's distributionally equal to the eigenvalues of a Wishart or matrix or an LUE matrix. So the Laguerre unitary ensemble, the eigenvalues are distributionally the same as the point process given by the increments of the watermelon weight. And it's also known that the edge of the point process, if you look at, let's say, the largest values, then it converges to the what is known as the Airy point process. And actually, you could have predicted the weight fluctuations, this k power whatever, 5/3, by understanding asymptotics of the Airy point process. But of course, the arguments are geometric, so you hope to actually go beyond these integrable models. But so I'll get there very soon, but just to sort of mention a result about this concentration. So this is the thing that we have for the process y and k. So we have understanding of x and k, and you can actually translate that to an understanding of y and k. So y and k are typically like 4n, the law of large number, and the increments are now k to the 2/3. So the probability that the kth point in this point process is not in this interval is actually, again, exponentially unlikely in k squared. And this is actually very similar to a rigidity statement that you might imagine about eigenvalues, that eigenvalues are really sort of very concentrated around where they're supposed to be located. So in this particular case of exponential LPP, because of this eigenvalue connection, you can also use that machinery. But it turns out that if you straightforwardly apply determinable point process techniques, you only recover an exponential in k bound instead of this exponential in k squared. But like I said, so the arguments that I presented sort of hopefully were geometric, seemed geometric enough, and it turns out that you can actually push these arguments to basically they were verbatim for the, let's say, the point to line setting. So here we were looking at disjoint paths going between two different sets of points, but you can instead actually sort of make the other endpoint completely free and then allow them to vary on a single line. So it turns out that the same arguments actually give you similar results in this new setting, point to line, where I don't think there are determinable connections to this point process. So the top, the yn1, the weight of the geodesic has a connection to an eigenvalue of an Eloy matrix, but not for the full ensemble. So just to sort of wrap up, so although we started with exponential LPP, the geometric arguments are robust, and actually it turns out that the main theorem just works under some strong local convexity of the limit shape and some non-trivial bounds on the non-random fluctuations, and some tail estimates on the fluctuation behavior for the geodesic. So we just assume something about the geodesic weight, and the geodesic weight profile having some strong curvature assumptions locally. It turns out that just having these two set of assumptions make all the arguments go through. So in particular, they should be verifiable for all known integral models of LPP where these things are known to be true. So I think I'm already out of time, so I'll just stop here. Yeah.
All right, well, thank you very much, Shirshendu. So I'll thank him.
Yeah, so
we have time for questions.
So I guess I should sort of maybe answer your question about the BK.
Sure.
So let me sort of, oh, sorry. Yeah. So somehow, so BK inequality tells us basically